Okay. Hello, everybody. It is about 5:30, so I'm gonna do the intro stuff. And yeah, so first of all, I want to thank you guys all for coming. This is the third version of this event that we've held. And I also want you guys to all give a round of applause for yourselves for being here, for your continuous education. You know, we're going to be talking about some very interesting things. Thank you. I love that. Yes, self-love, guys. It's good. So we're going to be talking about some very cool kind of things out here. I'm going to be talking to you about some of what we've been seeing for advanced applications in Retrieval Augmented Generation with vector databases. And then Vaibhav is going to be giving a talk about how you can make your models perform better than GPT-4. Originally, we had a third speaker. He has fallen off the face of the planet last week on Thursday, so I don't think he's going to be here. But if he does show up, we will have him give his talk on AI agents. He's building some cool things with AI agents. I'm going to go through a couple of housekeeping things, and then I'm going to get into the presentation. So number one, if you haven't gotten food, there is food up here. We ordered about 40 sandwiches. It looks like there's about 40 people here. I don't really know. But anyway, there's some food up here. And then this is the Unstructured Data Meetup is what we've titled it. It's run by yours truly here in Seattle. My name is Yujin Tang. And if you have something that is interesting that you are building and you want to share, especially if you are curious, especially if you're interested in sharing the technical details, please reach out to me. I do have my LinkedIn available. It will be on the QR code on one of these slides. Please reach out to me and be like, hey, I wanna talk about what I'm building. Our next iteration of this event is going to be planned for January because December is pretty packed, and I'm going to be off for 2 weeks, so you know, not going to do anything in December. All right. So with that said, I think that I will just get into it. Okay. So my presentation today is gonna. Oh, that's where this is. I was like, why is this like batteries? All right, so my presentation today is going to be about chunking, embeddings, and vector databases. So who here knows what any of these terms mean? Okay. Oh, you guys are all pretty. You guys all have an idea of what's going on. Okay. Does anyone not know what any of these terms mean? Okay, so a couple of you guys a little bit newer to the space. Cool. Okay. So I'm going to go to my first slide. So this is me. This is what I do right now. I'm currently a developer advocate at Zillis. I've put up a QR code there. That's the QR code to my LinkedIn. If you want to scan it, make sure you hit the 3 dots and you hit connect and send me like a little message so I know where you're from. I will give you a little bit about my background so you know like, why is this guy talking to me about machine learning? So let's see. So I started working at IBM when I was 16. And then I went to college at UNC. Shout out to my fellow Tar Heel over there, where I published a couple different research papers. And then I went to Amazon to work on AutoML. I originally had hoped to do a PhD after college, but I didn't get in anywhere. But Amazon was not a bad choice for me. So I went to Amazon. I worked there on their AutoML system, you know, generated some X million dollars of revenue. And I was like, okay, cool. Let's see what startups are like. So I jumped, I left. No plan. Started one startup, lost a bunch of money. Started another startup, didn't lose much money the second time. And but the second time around November of 2022, you guys remember what happened in November of 2022? Who can tell me what happened in that year? Come on, what happened in November of 2022? Someone raise their hand. Come on, this is an interactive talk. Ah, okay, yes, no hands raised, but I know that somebody knows the answer. Yes, ChatGPT came out. I was running a natural language processing API. You can imagine how that affected us. Okay. So that leads us to earlier this year where I joined Zillis, and Zillis is a vector database company, and that's what I'm going to be talking about today. For the last 6-7 months, I've basically just been building LLM apps, and so these are a lot of the learnings that I've got from doing that. Zillis is a vector database company. As I said earlier, we were founded in 2017. We've been around for a while. You guys have probably heard of Pinecone. We've been around for a little bit longer than Pinecone. We're based in Redwood Shores. And the repos you probably care about are Milvus. Milvus is an open source vector database, and if you have the skills, you can use Milvus for free there is no there's a commercially available license on it, basically. GPT Cache is one of our very, very popular tools. This has got over 1 million downloads in just the last few months. And GPT Cache is meant to be a semantic cache for your Retrieval Augmented Generation apps in production. And it is, we built it because we were basically running a $30,000 a month OpenAI bill, and we were like, hey man, that kind of sucks. And so we cached a bunch of the stuff, and then we dropped our costs by about 75% or more. The other one you might care about is VDB Benchmark, whatever. This is a vector database benchmarking tool. If you are checking out vector databases, I highly recommend you use this tool. We did build this tool, and it does say that we have the best performance on the data sets provided, but you can bring your own data sets, so you don't have to take my word for it. You can just check it out and do it yourself. The other one's probably not too important. So today we're going to be talking about why RAG, and then we're going to talk about chunking considerations, and then we're going to be talking about embedding models and strategies, and then I'm going to do a little bit about vector databases. This talk was originally scheduled for 30 minutes, but since there's only 2 of us talking, if you have Q&A at the end that goes a little bit over, we can probably go to about 40 before I pass things off to Vaibhav. Okay, so first we're going to cover why RAG. Who here knows what RAG is, or am I just like saying nonsense to you guys? Okay, so I need to define what this is because it seems like I'm just saying nonsense. So RAG is Retrieval Augmented Generation, and I'm going to tell you a little bit more about it in the next few slides. So the basic idea behind this is you want to use your data with a large language model, okay? So large language models, yeah, they're great, very powerful. Hey, welcome in. Please feel free to grab some food. They're great, very powerful, but one of the problems is they don't have access to your private data. And if you are trying to build a business, if you are working in an enterprise, very high chance you want to be working with your data. So what is RAG? What is fine tuning? So RAG is when you inject your data via a vector database like Milvus or Zillis. And here I've given a little diagram of what this kind of looks like. So your data goes into a vector database like Milvus, and then the LLM kind of sits on top of there and it talks to Milvus, and you have your query, and your query comes in, and your query goes to the LLM goes to Milvus, and then it gives you your answer back. And so this is really, really good for factual recall, for forced data injection, and for cost optimization. So I'll go over the cost optimization piece a bit in the next slide. For factual recall and forced data injection, the point of this is basically when you come and you give your query to the large language model, the language model is going to actually use the vector database as the source of truth for the data that it's going to return to you. Okay? So that's why the factual recall is really good with RAG. Okay, what about fine tuning? I always get this question, what is fine tuning? Fine tuning is not injecting your data via a vector database, but I just forgot to edit that. It looks like this. Your data goes with an LLM. You basically put your data into an LLM and you train it, and then that goes into a new LLM, a fine-tuned LLM, and you query your fine-tuned LLM. So the primary use case for fine tuning is style transfer. It's really good for saying, hey, I want you to talk like this. I want you to respond like this. Here's some data about, fintech stuff. I want you to use these vocabulary words, et cetera, et cetera, et cetera. So why is fine tuning bad for recall, factual recall? The answer is basically the scale of data that you have. If you think about the scale of data that OpenAI trains GPT on versus the scale of data that you probably have that's labeled and ready to fine tune with, it's probably, you're probably looking at maybe 0.1% or less. And so who here's taken intro to machine learning? Everybody has an idea of machine learning? Okay. So one of the things that you get from, one of the things you may understand from taking these classes is primarily what these models learn is the patterns in your data. So if you're adding 0.1% of your data, you're not adding a lot of patterns. And the way you can think about fine tuning is essentially adding a little layer, a little extra prompt, a little extra context in your prompt window. Okay, so that's what fine tuning is. That's what RAG is. And the takeaway from this section is basically use RAG to force the LLM to work with your data by injecting it via a vector database like Milvus or Zillis. Hi, feel free to grab a seat, grab some food. Okay, so there's a few things that go into building these retrieval augmented generation applications. And one of the first pre-processing steps, and perhaps one of the most important pre-processing steps, is chunking. And chunking is the process of splitting your data up into smaller bytes. You don't want to basically take an entire corpus and just say, embed this. Because then what are you going to get? You're going to get a semantic representation of that entire corpus, which doesn't actually help you with search. So you want to chunk things up so that you can increase the granularity of your search and get better results. The three, there probably are other considerations, but the three considerations that I break chunking down into are chunk size, which is the number of characters in your chunk, chunk overlap, which is the amount of overlap between your chunks, and character splitters, which is a specific way to split your data that is not necessarily related to exactly what the chunk size is. And you'll see this example in one of my examples. Okay, so the number one, I get asked so many questions about how do you chunk your data? How do I put my data into a vector database? How do I prepare this stuff? And so the number one question I always ask people when they ask me this question is, what does your data look like? How does your data look? And there are more than just these three types of, data, of ways to structure your data, but these are some basic ways to structure your data. So you may have data that is conversation data, which is, typically line by line. Maybe you're talking to someone at a call center, a customer service representative, or maybe you're texting your friends or something like that. So your conversation data is line by line. And in this case, you probably want to think about chunk size and chunk overlap a little bit differently than the other cases. So you're probably going to need less chunk size because your texts or your conversation, your little things that you're sending are probably not that long. And you probably don't need much overlap because you can always take the question and the answer and take them together and have that as metadata, but you may not need the overlap because you're kind of looking at one semantically sound, one semantic thing at a time, basically. The next one I have up here is documentation data. So documentation data, I'm just calling it documentation data, but you can think about this as basically any PDF that you're going to read. This could be a research paper. This could be, the Sec 10 or whatever, the 10Ks, whatever, the SEC stuff. And this data kind of looks like big ass chunks. There's just a bunch of big chunks of data. And so for this case, you need to think about what is your chunk size? What is a big enough chunk size that I can, get the semantic meaning, but what is small enough that I can have granular search? So you want to think about your chunk size when it comes to documentation data. And not only chunk size documentation data, you probably also care about your chunk overlap, because the chunking overlap, what that does is that allows you to keep the context, the relevance of the context between two different chunks. And so you can use that to map where chunks are, as well as keep the context between two chunks. And you may care about character splitters with documentation data. You may or may not. It depends on what exactly your documentation data looks like and how your paragraphs may be being split. And then the final one I have on here is lecture or Q&A data. And what this looks like is perhaps a question and a long answer, a question and a long answer. So this is going to be different from both because you got a little bit of a mix here, right? And so for this one, what you may want to do is you may want to use character splitters. You may want to leverage character splitters to really split your data into chunks. Perhaps you have something that marks when someone starts to talk or marks when someone ends their talk. And so at that point, your best bet is to leverage something that allows you to get complete answers and complete pieces of text, right? You want something that's semantically solid, semantically cohesive. So that's where you would leverage that. Chunk overlap may or may not matter depending on your use case, depending on what you're doing, depending on the size of your chunks, and depending on which part of the document you're at. So There are a lot of different considerations you can take. These are just some of the considerations. Something that I was asked about before is, what about code? Some people want to embed and chunk their code up. Code looks very different from all of this, and you're definitely going to want to leverage character splitters when you're doing code, especially if you're writing like Java or C++. If you're writing Python, a little more tough luck there. Okay, so we're going to walk through a real quick example. This is an example that I spun up using LangChain and Zillis. So Zillis is my company. We're a vector database company. Who has heard of LangChain? Everybody has heard of LangChain. Great. Okay. So LangChain is a large language model orchestration tool, and it makes chunking easy. It's kind of like, it's kind of like Llama Index. It has these like retrieval things in it that makes some of your chunking and retrieval easier. So obviously this is unreadable for you guys. So I'm going to kind of step one by one into the document. So for these examples, I took a Notion document that is about the different levels of software engineers. It goes from junior all the way to distinguished. And I basically asked the question, what makes a distinguished engineer? And from the chunking strategy 32.4, what that means is 32 characters per chunk, 4 character overlap. So you can imagine that this is completely useless, and you can also look at the results and see that this is completely useless, because all it does is return a bunch of the words engineer, because engineer is semantically similar to distinguished engineer. Okay, what if we move up a step? What if we go to 64.8? What happens then? Our first response is still completely useless. But now we see that there's one response in here that is not completely useless, right? It's like, okay, Werner Vogels, CTO of Amazon, is a distinguished engineer. It may not tell us exactly what a distinguished engineer is, but it gives us an example. It's like, okay, here you go. Here's somebody who's a distinguished engineer. And this is in the document. Okay, what about 128.16? Let's move up again. Now we see things like has achieved noteworthy technical professional accomplishments while working as an engineer. Senior software engineer, obviously that one is wrong and does not belong in there, but you can see that and you can process that out. You can post-process that out. Provides solid technical leadership beyond the company. And then once again, Werner Vogels. And then everything in the senior staff engineer list, plus generally 15, 20 years of experience. So, here we're getting back actually some of the results, some of the things that does make somebody a distinguished engineer, generally. Okay, where do we move on from this? What happens next? 256.32, now we're looking at 256 character chunks with 32 characters of overlap. So here we start to see things get a little bit more complicated, a little bit bigger. The sections are starting to contain a lot of new lines, a lot of this /XAO thing. And from the first one, it says, this will ordinarily require significant amounts of time over the lifetime of the individual given this distinction, blah, 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 Werner Vogels. Okay, so we know this is from the section. This is the right section. But as we go down, we can actually look at the last two, these two here, the last two page contents, and we can see that these are almost the same thing. And we can also see that the last one says everything on the staff engineer list, and the one above it says everything on the senior staff engineer list, right? So they're just slightly different, but they almost say the same thing, so we're getting the same results back. But now what this means is we've kind of stepped out of our territory. Now we have things that, in the last one we had more useful stuff, and now we've kind of got too much extraneous information. But what about 512? What's 512.64 look like? So I'm not going to read all of these out to you because this is starting to get too long to read out, but if you look at the first one here, you'll see that this content, the first one, once again mentions Werner Vogels. And actually, this contains all of the information that I have listed under the distinguished engineer chunk. And so 512, the first result, actually gets you all of the information that you need. So from these examples, what I want you to understand from these examples is basically the 128 and the 512 both work, but your choice for that should depend on what you need from your responses. For example, if you would like to give responses one at a time, one piece at a time, then you should go with the 128. However, if you want an entire chunk and you want to return all of your entire chunk in your use case, and you're imagining that whoever's using your tool is going to want that, then you want to go with the 512. So your chunking strategy depends on what your data looks like and what you need from it or what the end user is going to need from it. Okay, so we've covered chunking. Now we're going to talk about embeddings. Before I go into embeddings, does anyone have any questions about chunking? Yes. You can also chunk by words. It is just easier to chunk by characters, and so that is the default implementation. If you would like to chunk by words, typically you would use something. Well, Llama Index uses something like NLTK. You could use something like Spacey. The challenge of chunking by words is that you would probably need another model in order to model that, in order to get those for you. You could just say, okay, we're going to split on spaces. Like every word is a space. So, if you want to do that, that's also fine. But typically there are a little bit more considerations with that. And so that's why the default is characters. Yes, sir. Yeah, so you're talking about basically, yeah, you can. But A, the more data you want to fine tune on, the more expensive it's going to get. And B, as you use the same data point over and over again, the impact of that data point becomes, you get diminishing returns over time. So you can do it, maybe not the best idea. That is a very, very difficult question. And if you can solve that question, I'm sure that you can probably build the next unicorn. Any other questions on chunking? Okay, we're going to move on to embeddings. Cool. Okay, so let's examine some embeddings. There are about 3 things that I think about when I look at embeddings. One is picking a model. Number 2 is what you're going to embed. And then number 3 is the metadata that you want to include with your embeddings, okay? So in this section, we're going to first go with picking a model. Here are some examples of places where you can get embeddings models. Hugging Face, sentence transformers, very popular library, works pretty well out of the box, and one of my favorites because it's free and it works decently well. So, Hugging Face sentence transformers, check it out. MPNet is pretty good. I think that's 768, and then Mini LM is pretty good. That's 384. That's the number of dimensions in the embedding. I'll cover dimensions in a second. And then OpenAI, everybody knows OpenAI by now probably. And then there's AI Blocks. So AI Blocks creates this open source thing called LLMware. And they are, as far as I understand, they are specifically aimed at fintech. At least that's what they're doing right now. They may or may not pivot. They're a very early stage company. So I'm not entirely sure. And then there's Llama 2. You guys have probably seen Llama 2. If you follow me on LinkedIn, you have seen that I tried to get Llama 2 running on my 16 gigabyte Mac and crashed. So yeah. And then there's PyTorch. Everybody probably knows PyTorch. PyTorch is, kind of like Hugging Face, and it contains a lot of models that you can download, you can use, and you can get the vector embeddings from, because PyTorch allows you to easily work with your models as if they're just like, layers, and you can just like a list, and you just cut off the last layer and you get your vector embeddings. So, I forgot to comment on this earlier, and I don't know if I have the slide for it, but vector embeddings are the output from the second to last layer of an embeddings model. And the dimension of a vector embedding is the number of nodes in that layer, the number of neurons in that layer. So why is it the second to last layer and not the first layer or the second layer or whatever? Because as you pass data through a machine learning model, it learns semantically about your data. And the second to last layer includes all of the information that the model learns without applying the model's predictions, which is what happens in the last layer. And then, you guys probably recognize Anthropic. They have Claude. So yeah, these are just some examples. There are many, many more options. These are just some examples that I like. Okay, what about embedding strategies? So semantically, these are actually probably more like tactics, but we call these strategies in the industry for some reason. So level one is you just embed your chunks directly, right? We were talking about just chunking earlier. You just take your chunks and you just blindly embed them, and you're like, all right, good enough. Number two is you start embedding sub or super chunks. And so what that means is you're going to chunk your data maybe into paragraphs and you embed a sentence. Or maybe you chunk your data into sentences and you embed a paragraph. And then you just tag the text with that embedding. And so this strategy, Llama Index, calls big to small or small to big. So you may also hear it referred to that way. And the point of this is basically, if you would like to search and get the context around the answer for your whatever is semantically similar, then you're going to want to attach paragraphs to sentence embeddings. If you're going to want to get something based on its larger semantic meaning, but you want to get the fine-grained results, you are probably going to want to attach sentences to paragraph embeddings, okay? So those are the kind of two use cases for these strategies. Number three is you want to incorporate chunking and non-chunking metadata. You pretty much, if you are using Milvus at least, I can't speak for every other vector database, but if you are using Milvus or Zillis, you can include metadata for filtering. And this is incredibly useful for things like non-chunking metadata or chunking metadata. So as I was referring to earlier in the small to big example, right? You're going to embed an entire paragraph and you're going to want to extract sentences. You probably want to know what sentence number is that. In this case, also the larger paragraph would be the large paragraph. What is a section header? Where in the document are we? What is the paragraph positioning? As in, is this the first paragraph in the section? Is this the second paragraph in the section? Maybe you embed an entire section and you want to extract paragraphs. I'm just giving an example of sentence to paragraph, but paragraph to section is also perfectly fine. Other things you may want to look at are non-chunking examples, such as the author of the document, the publisher of the document, the organization the document was from, or maybe even role-based access control. So if you're who is a software engineer? A lot of software engineers. Okay, so you guys all know about, you guys have all worked at enterprises. Everyone knows what role-based access control is, right? Yeah, so this thing is, something that may be important for your chunking data because maybe you want to filter off of certain roles. Now, in Zillis, we have this applied, but perhaps you want to have more fine-grained results, and that's when you use something like this. So the takeaway here is that your embedding strategy depends on your accuracy, your cost, and your use case needs, okay? Okay, before I go into vector databases, any questions about embeddings? Oh, yes. What? Yes, so he asked a question about whether or not embeddings would be good for dealing with memory or context over time. So you, sir, are going to love this next section about vector databases because that's exactly what that's for. Any other questions about the embeddings before I dive into this? Yes, sir. Okay, so you are getting embeddings from the deep learning model. So whatever your chunks or whatever, you feed it into a deep learning model, you cut off the last layer, and you get the output from the second last layer, and that's an embedding. The large language model does not necessarily understand how to decode those embeddings. Large language models are downstream from this. This is upstream. This is pretty early in the process, in the RAG building process. So you actually get your embeddings, and then once you have your embeddings, you put them into vector databases. And so this is why I kind of like did the stepping of chunking, embedding, vector database. And then once you have them in the vector database handles all of the similarity search for the embeddings. And so that's why I was talking about metadata. So you want to store the relevant metadata. Perhaps it's a link to your image. Perhaps it's a link to your video. Perhaps it's your text, your raw text, whatever, something like that. So you want to store that in the vector database as metadata. So when you pull that information back, you can give that information to a large language model, and the large language model can then formulate that into something that is human readable. Does that make sense? Indeed, yes. Large language models get natural language, yes. Any other questions? Yes. Yes. Can you shout? Good question. Yes, it is not limited to just text. You can do it on images. You can do it on videos. You can do it on basically anything you can think of. The limitation is that in order to get an accurate embedding, you must use an embedding model that is trained on the type of data that you want to embed. So if you want to embed video data, you must use an embeddings model that's trained on video data. Does that make sense? Why would you? Well, you would only do that if you needed to do that. You don't use technology for the use case of using technology, right? Oh, what's the added benefit you get from doing the embedding and then using the vector database to compare the embedding? Okay, so the added benefit is that if you are doing something that uses similarity search and wants to compare to unstructured data, that is when you would use this. If you were not doing similarity search and you want to say simply you want to give a video to a large language model and you want to say tell me what this video does, then you can skip the step entirely. This is only for when you want to do things that require the use of similarity search. Does that make sense? The vector, can you shout again? I'm sorry. Oh, yes. The is things for similarity search and what the vector database can do well. The real use of embeddings is that it allows you to compare two types of unstructured data. Okay, cool. I hope I'm not running too far over. Okay. Okay, so now we're going to talk about vector databases. Vector databases provide the ability to inject your data via semantic similarity. And when you are picking a vector database, your considerations probably include scale, performance, and flexibility. So before we talk about vector databases, I'm going to cover this kind of, who's here seen this image? Okay. Okay, so I'll cover it. Not everybody's seen this. Okay. So this is essentially how semantic similarity works. We are doing math on things that are not numbers. And the way we're doing that is we're basically comparing the vector embeddings. So I want to make a couple notes here. Number one, you will never see two-dimensional vector embeddings in practice. If you see this in production, wherever company you're at, leave and find a new job as quickly as you can. Number two, nobody's ever going to use Manhattan distance. And if they are, they're going to have a very, very, very good reason. So yeah, those two things, make sure you keep them in mind. Number three, you will see that the words queen and woman and king and man have the same value on the first dimension here. I want to stress, this is very, very important to understand. I want to stress that this does not tell us anything about what that dimension means. That dimension does not mean gender or sex or whatever. That dimension is simply the same value for these words in this case. It could be that dimension assigns a value of 0.5 to words with 5 letters and assigns a value of 0.3 to words with 3 or 4 letters. We have no idea what the dimension means. We just know that they mean the same thing along that dimension. Okay? Very, very important to understand. I want to get that point across. So now that we have all these things, let's take a look at how the math works. So we'll start with queen. Queen is 0.3, 0.9, right? And then we'll subtract woman, which is 0.3, 0.4, and we'll arrive at 0, 0.5. And as people, we can probably guess that this means something like royalty or something like that. But that does not necessarily mean that the model knows that. Okay, so that's why I didn't put a word here, is because these words represent what the model knows, not what we may guess to be true. Okay, and then next we're going to add the word man, which is 0.5, 0.2, and we're going to arrive at 0.5, 0.7, which corresponds to the word king. Okay, so basically, if you weren't really following along, the whole point here is you can do math on things that weren't originally numbers by using vector embeddings. So where do vectors come from? Oh, I did have this slide in here. I covered it earlier, but I I will cover it again for you guys. So essentially you have your knowledge base, some sort of image, some sort of video, some sort of audio, some sort of text, something like that. You're gonna feed it into a deep learning model. You're gonna cut off the last layer. And those are the vectors. And then you're gonna put that vector into Zillis or Milvis or some sort of other vector database. So I also want to just show you guys what an entry into the vector database looks like, right? So I get a lot of questions about what this kind of data looks like, and I find that it's very helpful to kind of just show you what it looks like straight up. So you'll see there's ID. That's important. That's how we pull by ID. You can pull your entries by ID. This is how you do upserts, deletes, and inserts, right? And then the embedding, which is how you do the queries. This is search. This is the similarity search parameter. This is what allows you to compare the semantic meanings. And then you've got the date. And for this one, I have a paragraph and some other like random metadata. This is something that I pulled from one of my recent projects where I scraped towards data science and made like a chat bot for towards data science. So that's what this is from. And the main thing I want you guys to get from this is ID, embedding, some sort of metadata. Okay, I'm not going to read this entire slide. So if you want it, you can take a picture. But I want to answer the question of why would you use a vector database instead of a SQL database or a NoSQL database, or like a vector search library put on top of one of these, right? So you guys have probably you guys know about Mongo, you guys know about Single Store, you guys know about these tools, right? Everybody, okay. And you guys know that they're like SQL, NoSQL underlying databases, right? Everybody kind of knows. Okay, cool. So as you build databases, as you build systems entirely, as you build systems, you make design decisions according to what your system's main support is. What do you mainly need the system to support? That's how you make your design decisions. So when you build a SQL database, when you build a NoSQL database, your design decisions revolve around how do I get the exact response, or for SQL sometimes, how do I effectively join multiple tables to get relationships? So these are not the considerations that you need when you're working with vector data. When you're working with vector data, your primary consideration is how do I perform 100,000 compute in less than 0.1 milliseconds? Because vector data and vector data query is almost entirely revolving around how do you compare two vectors, which is very computationally expensive. And if you are a SQL database or you are a NoSQL database, you are not built to handle that computational intensity. And that's why these things do not scale very well. Okay, what about vector search libraries? Who here has heard of FAISS? F-A-I-S-S. Just two people. Okay, what about HNSW? Just a couple of people. Okay, so these, okay, so I guess this section isn't terribly important for the rest of you guys because you guys haven't heard of these libraries. But I will cover this very briefly for you guys if you're interested. So vector search libraries like FAISS, like HNSW, they provide you the functionality to run vector search, but they lack the infrastructure and they lack a dedicated infrastructure, essentially. Hardware optimization and resource optimization are very, very important when you are running things that are very, very computationally expensive, as vector databases are. So vector search libraries lack the infrastructure to help you scale, deploy, and manage your apps in production. Okay, so what is Milvis or Zillis ideal for? Once again, I'm not going to read this slide, so if you want, you can take a picture. But essentially, Milvis or Zillis, Milvis, I'm just going to talk about Milvis because Milvis is the open source one. So Milvis is the only distributed system vector database that's out there, at least as far as I know. If I'm wrong, you can feel free to correct me. And Milvis, in that sense, Milvis is really built out for scale, and it's really built out for high availability for multiple regions. If you think about CockroachDB or Cassandra, is kind of similar in that aim of being scale out and being easily available and accessible across time, and lets you basically add data at an almost infinite scale. So the differentiation, as I was saying earlier, cloud native distributed system architecture. We originally built Milvis 1, And then we went to about 1,200 some people, 1,200 some companies, and we were like, hey, how's this working for you guys? What do you guys want us to put in the next one? And so we figured out that the main problem for many, many people is scale. The main problem is that when you're building a single instance scale up database, you face the problem of running into the biggest CPU or GPU that you have. And once you have that, you have to spin up more, and then they don't talk to each other. There's no write consistency. You have to do data migrations. There's a lot of pain that's involved with dealing with scale-up databases once they hit a certain level, which is why Cockroach and Cassandra exist for SQL and NoSQL, and this is why Milvus exists for vector databases. One of the other things that makes Milvus truly interesting is that we have an actual separation of concerns. So I think, oh no, it's not in here. Is it in here? It's not in here. Ah, wow. Okay, I thought I had this in here. Well, there is a, I do have this somewhere. If you guys want to see, there is a architecture diagram of Milvus in here. So Milvus, there are three concerns when it comes to doing search, and those concerns are indexing, which is how do I create the way to access my data? Data or data ingestion, which is how do I actually get my data? And then querying, which is how do I search my data? And so Milvus has a true separation of concerns on these. Each of these three things are handled by different nodes, different worker nodes, and different coordinators. And then the last thing I have on here is that we have very, very scalable index creation with 512 megabyte segments. What this means is that every time you put 512 megabytes into the system, or there's like some sort of pause between you putting data into the system, we create an index on that, which means that search or query time is extremely efficient at scale. And the way this happens is, if you just think about this, we're going to do a little bit of math. If you have 100 gigabytes of data, would you prefer to do 100 gigabytes in sequence and search that in series, or would you prefer to perform 200 parallel searches over 512 megabytes and aggregate that? Well, one is a linear approach, and the other one is almost constant time. So you probably want to go for the parallel approach, and that's why we have decided to make our indexes over those segments. Okay, so the takeaway here: vector databases are purpose-built to handle indexing, storing, and querying vector data. And Milvus and Zillis are specifically designed for high performance and billion-plus scale use cases. And here I want to leave you guys with a couple other QR codes. So one is an open source benchmarking tool. That's Vector Database Benchmark. Check it out, download it, use your own data. Don't believe things just because people say they're true. And then another one is an advanced hands-on LLM/RAG app building tutorial. This is something that I built with LangChain and Llama Index, primarily Llama Index. And what it does is it allows you to do querying on multiple documents by routing to those documents based on keywords. This is somewhat similar to something that you may actually build in an enterprise environment. So that concludes my talk.